Today we're looking at electromagnetic waves and polarization. So first off with electromagnetic waves, so those are made up of both electric field and magnetic field vectors together that are working perpendicular to one another. So if the electric field is going in the y-axis, then our magnetic field is going to be acting in the x. And so again, they work together and we wind up with a wave, and they are a transverse wave, and so they have all the same properties as far as like wavelength, troughs, crests, stuff like that. Come on, there we go. Okay, so where this electromagnetic wave is going to come from is the fact that these waves are actually self-propagating. So if we look at the example of a broadcast radio or TV antenna or something like that, those are normally stuck relatively straight upward. That's why like broadcast towers are really, really tall. And what winds up happening is there's some kind of potential difference applied to that tower that causes the electrons to constantly move up and down. And as electrons move, remember that's going to create a difference in both an electric field and a magnetic field as well. And so as those electrons are changing, because the change in height, that's changing where the thing is, so that changes the electric field. And then because we have a moving charge, that creates a magnetic field. Now as those electrons keep moving, that causes the field to fluctuate. And so remember that a changing magnetic field induces an electric and vice versa. So what we wind up getting though then is this constant induction of field, and so that's how we get an electromagnetic wave, because the electric field and the magnetic field are going to keep propagating each other until it hits something that causes that field to decay. So this is why light is able to travel forever in a vacuum, because it doesn't require its own medium, it's self-propagating. Now if it hits something, then it could cause that, it could disrupt that field and turn it into some other kind of energy. But until then, it's just going to go on and do its thing. And yada yada. So don't have to worry too much about this, but just as a heads up as to where this stuff comes from. So in the past we've talked about the permittivity of free space, and so we have both the permittivity of free space for electric and magnetic fields. And so in a vacuum, which is what we've been using them for, through Maxwell's equations, which we don't have to worry about, but just as a neat little tidbit, we can wind up getting the speed of light. If you look at the units that these are made up of, it comes out to 3 times 10 to the 8th. So that's essentially where those constants come from, and where the speed of light comes from, is it's all related to each other there. So just a fun little fact there. Alright, so on these, pause it real quick when I get there, and so you can have a little bit of time to answer. Alright, so electric field is produced by a separation of charges, or by, again, we can have it the kqqq over r squared, so that would be the separation of field, or sorry, kqqq over r, or whatever it is, I can't think of the equation, but you know that, you put charges apart from each other and you can get a field produced between them. The other way to do it though, remember, is going to be a changing magnetic field, not a constant one, it does have to be changing. So that one's going to be A. For this one, changing electric field will produce. So, again, this one is going to be a changing magnetic field, because a changing electric field isn't going to produce itself, it's not going to do anything with gravity, and it will be a changing magnetic, it's not going to be constant, so that knocks D out as well. So this one is going to be B. Alright, so just some general properties of electromagnetic waves. So again, we know that electromagnetic waves, when they're traveling in a vacuum, are going to be moving at 3 times 10 to the 8 meters per second, and that velocity is equal to wavelength times frequency, or V equals F lambda. But electromagnetic waves are going to be a little more complicated than other waves, because we can have different types depending on what is causing these things. So we've got the electromagnetic spectrum, which there are posters around the room that you can look at. Some of those posters will be taken down, though, for quiz and test days, just as a heads up. But anyway, so we've got the whole electromagnetic spectrum, and everything on here is an electromagnetic wave. Everything from radio waves to the visible spectrum of light, which is a teeny tiny sliver, down through gamma rays that, turn you into the Hulk, and that's obviously what happens. You clearly, don't get cancer and die immediately. You turn green and you get angry. But anyway, so we've got our whole electromagnetic spectrum here, and it's arranged in either increasing frequency if we go to the left, or increasing wavelength if we go to the right. So remember, V equals F lambda, so assuming we're in a vacuum, if one of those values goes up, so let's say frequency goes up, that means that wavelength has to go down. So it's just a matter of remembering basically which way the frequency increases, which way the wavelength increases. Um, Probably the easier way to do that is to remember that energy is based on frequency, which we'll get to more heavily in next unit. So if you need to remember, things like gamma rays are obviously going to have a lot more energy than radio waves will, just because, you know, you have radio waves passing through you all the time. It's not a big deal. But you get gamma rays passing through you, that's not going to be a good time for you. So, we've got both of those things going on there. Alright, so light with a wavelength slightly shorter than 400 nanometers is called. And so this is, 400 nanometers, by the way, before you pause and do this, that's going to be roughly the, roughly blue light. So this, we're talking shorter than light on the visible spectrum. So whenever we go to look at that, remember, if it's, if the wavelength itself is going to be shorter, so if we go back to our spectrum, we're going to be moving leftward here. So if we've got 400, which is violet, and we move left of that, that's going to be ultraviolet. If it was asking for decreasing frequency instead of a decreased wavelength, then we would have infrared as our answer there. But because we were looking at a shorter wavelength, it's going to be UV. Let's see, electromagnetic waves travel through vacuum with, and so this one is going to be D, the same speed, 3 times 10 to the 8th. Remember, the only thing that's going to affect the speed of a wave is the medium that it travels through, and that's true regardless of whether it's a mechanical wave or an electromagnetic wave or whatever it happens to be. And then for this one, again, the wavelength and the frequency aren't going to affect it, it's just simply the medium it's in. And then different types or different frequencies of waves will travel different speeds in different medium. So like we saw with different colored light, they're going to travel, they have different indices of refraction, which means they have a different different speed, and that's true for all wave types. But in a vacuum, everything goes at 3 times 10 to the 8. Alright, which one of these is not electromagnetic? Hopefully you can look at these real quick and see that that's going to be sound waves. So microwaves, gamma, and radio, those are all definitely electromagnetic. Alright, which of these are going to be in order from longest to shortest wavelength? So just take a second real quick to look over. So as we look at the electromagnetic spectrum down below, longest we can see is going to be radio waves because those have the biggest ones. So that's either going to be C or D. Shortest are going to be gamma. So that knocks C out because it has gamma over ultraviolet. So D is going to be the answer there, and that that checks out because we've got we've starting with our radio waves, then infrared is next, then visible light after that, and then X-rays. So that all went in according to plan. Whereas C went radio to IR, then it went to gamma, and then back to ultraviolet. Okay, for electromagnetic wave, frequency is multiplied by wavelength is called this waves, and then this one, hopefully you know, is going to be speed. Technically velocity, but if we don't have a direction, speed works. Color with the highest frequency. So again, hopefully by now you know that red light has the longest wavelength, blue light has the shortest one, so even without seeing the electromagnetic spectrum, because blue or violet has the shortest wavelength, it's going to have the highest frequency. So on this one, D is going to be the answer. Longest wavelength, again, same sort of thing there. Red, hopefully that should be common knowledge by now. If it's not, just throw it in the back of your brain. That red light has the longest wavelength, lowest amount of frequency. Blue light has the greatest wavelength, or smallest wavelength and greatest frequency. So this one is going to be B, red. Alright, wavelength wavelength of light that has a frequency of 6.2 times 10 to the 14th hertz is. So again, I know that V equals F lambda. And so the velocity, so we can, since it doesn't say that it's traveling in a medium, we can usually assume that it's going to be a vacuum. So 3 times 10 to the 8th equals 6.2 times 10 to the 14th times lambda. And so when we solve for lambda, you should get either 4.84 times 10 to the minus 7th meters, or you could do 484 nanometers. Whichever way you do it is fine. And then just as a heads up, this is going to actually be blue light. So if you were to check the EM spectrum, that's what you'd see there. Alright, frequency of light whose wavelength is 600 nanometers. So again, V is F lambda, V is 3 times 10 to the 8th again, equals, we're looking for a frequency, and then we need 600 times 10 to the minus 9th, 9, or 6 times 10 to the minus 7th. Trying to write and think two different things at the same time. When we do that math then, you should really only get one type of answer. That's 5 times 10 to the 14th hertz. Throw a line there to make it a fancy Z. Alright, then polarization. So, electric field vectors are going to be perpendicular to the motion of the way which we call the plane of polarization. So basically, if the electric fields are going up and down like this, we're going to call the plane of polarization the horizontal axis. Now, all light waves are going to have completely random polarizations because it's based on what direction were those electrons moving at the time that that light got emitted. And so, in a case like, a natural case like the sun or something like that, those electrons are going to be going all over the place. So we have unpolarized light because there's no, single or even predominant plane of polarization for said light. So most of the interaction that light has with matter is due to electric field vector. The reason being is that most atoms aren't going to, do anything with magnetism or the magnetic field or stuff like that, whereas everything is going to have electrons, which is going to mesh with it. So the electric field vector is the one that light really is going to matter and pay attention to. So when we talk about polarization, we only care about what's going on with the electric field vector. The magnetic field vector is still definitely there, but it's not going to be doing nearly as much. So basically, what winds up happening is as those electric fields are moving up and down, and they hit something, the question is, will that thing that they hit be able to absorb that energy or not? And so to be able to absorb it, the electrons within that sample that they hit are going to have to be able to move with the field. If they are, then great. That's where we wind up with light being stopped. If they're not, then that light is going to be able to travel through. So if light hits any kind of solid object, and it doesn't have to be a conductive material, if it hits any kind of solid object, we can get electrons moving even just a little bit through that sample. So all solid objects, for the most part, are going to basically stop light just because, the light hits it and those electrons can move whatever way they want. Some materials are going to be translucent just because, for whatever reason, certain wavelengths of light aren't going to be affected by it. That stuff is above my head. If you decide to take, advanced physics courses, you'll probably learn more about atomic light wave interactions and stuff like that. But that's above my pay grade. But if we can get a translucent material that is basically made up of really long strands, so we're talking about here organic polymers, depending on how they're oriented, we can actually get that light to become polarized. So if a certain polarization of light hits it, depending on how it's oriented, those waves may be able to or may not be able to travel freely through. So basically what happens is here we've got unpolarized light on the left, and this is going to represent the electric field vectors. And then on the right, we can see that after it's gone through this polarization filter, we've gone from having unpolarized now where there's just simply one direction of light. And so if you look at the orientation of that polarization filter, you can see that it's perpendicular to there. So where we mentioned the axis of polarization, remember that's perpendicular to the electric field. So if we can get a polarization or polarizing filter that lines up with the polarization axis, we wind up with polarized light. And so the reason that this works is as the bold one is going, since that's moving up and down, when it hits this filter, based on the polymers that make up these polarization lenses, if it tries to start making the electrons move up and down, they have a teeny tiny amount of space to do that. So they're really not going to be able to move. So because the electrons within this within the filter aren't able to affect those polarizations of light, that light's able to pass through because it's uninhibited and it goes through to the other side. Whereas the others that are within the plane of polarization, whenever they hit it, the electrons are able to move in the horizontal position. So they're able to do that and basically like absorb that wave by having the electron move. It negates the electric wave or the electric field, which then, since there's now no more electric field, there can't be any more magnetic field, so there's no more light. So it's kind of similar to like if you were to, let's say you were throwing a disc or something and you're trying to get it through a picket fence. Normally you try, like if the picket fence were lined up like this, you would try to throw the disc so that it's traveling in the direction so it would slip between the fence. And it works the same way for polarization, but it's the opposite. So like if you had a picket fence like this, you would want to throw the disc this way. Because of the way that light interacts with it, it's going to be a little bit weird, or a little bit backwards. And again, it all has to do with those electrons moving in order to negate the electric field. If they can move to negate it, then that electric field gets knocked out, which knocks out that particular wave of light. If those electrons cannot move, then that light is able to pass through. So where this really comes into play is with polarization. So those of you who have polarized sunglasses, and it's actually kind of easy to tell if you have polarized sunglasses or not, because you can, if you look at like the water, or you can look at cars when the sun's shining down, so cars just sitting in the parking lot or on the highway or whatever, when the sun hits it and that light gets reflected light, and again, this is kind of above my pay grade, had to do a Google search for this and not fully understanding what's going on. But when light hits a surface, it polarizes it all in one direction because that reflected light is that same energy that came and hit the atoms, and those atoms are re-releasing that energy off. So it comes off in one polarization or one plane. And because it's very predictable what that plane is, when engineers design sunglasses that have a polarizing filter on them, they design it in such a way so that it's going to cancel out whatever that reflected light is or whatever that glare is, so that you can see things clearly. So like people out on the water will do this because A, it's a lot less bright, but then also if somebody's like maybe a fisherman or something like that and they're fishing in a river or a stream, that glare produced by the sun can keep them from being able to see through the water. Put on polarizing filters, all of a sudden now you don't see that reflected light because it gets canceled out by your sunglasses, and so they're able to see the fish in the stream. And it also works on the road because it's a lot easier to see when there's not glare in your face all the time. If you have another thing is if you have two polarizing filters, since they cancel out that particular wave of light. So let's say we have the filter going and now the wave is like this. If I put another filter perpendicular to it, it should, for the most part, cancel out that light. Now, there's some weird stuff that happens, which is way above anything I've ever tried to know, that, like, it works kind of weird and wonky. So there's going to be some weird things happening when you have multiple filters. But basically, if you can tell you have polarized lenses, if you take one lens that you know is polarized, put up with another, if you rotate them with a light source in front of it, you should be able to see that light source brighten and dim as you move it, because you're filtering out more and more of those light rays that are able to come through. So to do the math for the intensity of light that comes through a polarizing filter, we want to use this equation here, I equals I naught cosine squared theta, where I is going to represent the intensity. So this is the intensity of the light that comes out. This is the initial intensity of the light, and then cosine squared theta. The intensity, I think, does have a unit, but we're not going to be bothered with that. I think calculus gets more into it. For us, it's just simply like you have this much light coming in, it passes a polarized filter, how much of that light made it through. So it's really just going to be fractions and ratios and stuff. One thing to note, though, is that if you ever have unpolarized light passing through a filter or passing through a polarizer, it is reduced to 1/2 the original. So in order for this to work, that light has to be polarized. Otherwise, if it's unpolarized, then we just get simply 1/2. Alright, so what is the principle responsible for the fact that certain sunglasses reduce glare from reflected surfaces? So that's going to be polarization. So again, in order to reduce that glare, we have to cancel out those wavelengths, and so that's going to be polarization. Refraction is not going to be it. Neither will diffraction or total internal refraction. Just polarization. Which component of electromagnetic wave interacts most strongly with matter? And so that one's going to be the electric field. So the gravitational field, remember, is one of the really weakest forms of fields that we have, or forces. So that's not going to be it. And then between electric and magnetic, since everything has electrons and is affected by electric fields, it wins out over magnetic. Alright, unpolarized light passes through two polarizers. The axis of one is vertical to the axis, and the other is tilted 30 degrees from the vertical. The intensity, incoming intensity is I naught. Want to know the final intensity. So go ahead, pause, work it out a bit. So for this one, so I know that initially my I naught light is coming, it's got all kinds of directions to it, it's unpolarized, so it's going all over the place. So it's going to hit the first one, the first filter that has vertical stuff. So when it comes through here, the only rays that are going to make it through are light rays going in this direction. So to begin with, remember that all unpolarized light that passes through a filter is going to be reduced by 1/2. So at this point, we have half of our initial intensity. Then it goes through a filter that's tilted 30 degrees from the vertical. So something like that, roughly. So to calculate that, remember we have I equals I naught cosine squared theta. I prefer to do it like that. If you prefer to throw a square there, by all means go for it. So at this point now, the initial intensity of our light is going to be 1/2. So intensity equals 1/2. Theta, we know is going to be 30. So if we do cosine squared theta, where theta is 30, that comes out to 3/4. So 1/2 times 3/4 is going to be 3/8 of our original. So we get C then. Alright, so any questions? Feel free to email me and let me know.